In the first lecture, I talked about dark energy from the observational point of view, the second about dark energy from the theoretical point of view, and now I'll talk about where the rubber hits the road when you try to compare theories to observations and data to models. So how do you actually go about doing this? What are some of the common tools that people use, and what are some of the pitfalls along the way, in particular systematic uncertainties? So there's this quote from a famous non-physicist about comparing observations to theory. So in theory, there's no difference between theory and practice, but in practice there is. And in particular, systematics is the big hurdle in doing this. So I'm going to take you through some more pedagogical slides of what you actually do to solve the dynamics of dark energy and how you actually do these calculations. And I give references so you can follow along to actually go through the details more at leisure. So we've talked about the Kleingordon equation for the dynamics a number of times, that this is just the Lagrange equation basically for it. And how did I suddenly, here we go. Okay, so it's basically like Newton's second law. To solve this numerically on the computer, it's convenient to transform to other variables, basically the square root of the kinetic energy and the square root of the potential, and also to work in terms of a logarithmic time variable, the log of the scale factor. And if you do that, you get a system of equations. And if you remember your mathematical physics, this is what's called an autonomous system of equations, in that the time variable never explicitly appears. You have a derivative on this side, but you don't actually have any indication of the time factor on the right-hand side. And these are coupled equations. Y appears in the x equation and x appears in the y equation. But again, because the time doesn't appear, this is a very simple system of equations to solve. And then I've defined some of the other parameters here, in particular the potential slope enters through this lambda parameter here. So this was written down with great clarity by Copeland, Little, and Wands back in 1998, and I recommend you look at that paper if you want to go through it in detail. But again, it's very simple to put this up. If you want to modify your dark energy by putting in negative kinetic terms, by putting in couplings and so forth, you can still put it in these terms pretty easily. So you can go through and just numerically solve this system of equations. It's convenient to transform either at the end, or you can actually transform these equations at the beginning into things that are closer to the observables. So for example, you might want to transform it to what's the actual energy density in the dark component, or what is the equation of state of the dark component, and look at the dynamics, the behaviors in respect to those variables. You can add more equations. For example, you can add an equation to directly talk about how this gamma parameter, how that is evolving in time. And then you're getting the WW prime, the phase space behavior of the dark energy, very directly. And so, for example, this is what we did with the paper with Robert Caldwell. When we developed the freezing and the thawing models, we solved the system of equations, adding a system specifically for W prime, and looked at the relationship between W and W prime to define these freezing and thawing regions. You can go even further. You can actually solve directly for distances and so forth using these sort of autonomous equations. And you can basically, in a single program, then get out all the observables that you really want to deal with. You're doing numerics, so you want to use basic good numerical practices. So you should look at things like Numerical Recipes book on this. In particular, the things that you want to pay attention to are your initial conditions. You can, for example, either start off in what's called the frozen state, so you just start with no kinetic energy at some value of the field. And that's, of course, a very good solution for the thawing models. For tracking models, that's not a good initial solution, but you will fairly quickly go on to an attractor trajectory. And so you have to give it enough time in the integration to avoid the initial transients. For a tracker trajectory, if you're interested in solving those potentials, you can actually just put in the tracker solutions which you can get analytically as your initial conditions as well. But the key thing is to integrate long enough that your initial transients go away. You want to shoot forward in time. It's tempting to say that we know the conditions today, so let's go backwards. But again, that tends to be numerically very unstable. And again, you read numerical recipes, they'll tell you things like you use fourth order Runge-Kutta. You can download standard programs to go ahead and do that if you want to then play with your very own dark energy model. There's some interesting little tricks you can play. For example, if your model has the energy density and the dark energy being monotonic in time, monotonically increasing, for example, you can actually switch to that as a time coordinate, and then you just define the present by a particular value of the dark energy density. So you can say the present is when omega phi is 0.72. And again, that becomes your time variable. You can just do all your solutions in terms of that variable. So I've shown two graphs here of these numerical solutions for actually a fairly complicated potential. It's a potential that has some false minima in it. This is the Albrecht-Skordas potential. So it's basically like a polynomial prefactor times an exponential. So it has these extra minima, and these extra minima give you oscillations in the equations of state. So here I've shown W as a function of the time variable as a function of A, and you can see these oscillations here. One of the points is, though, in order to get observable oscillations as you go toward the present, you actually need a high value of dark energy density at early times, which is clearly ruled out, as Wayne mentioned, by the CMB. If you get down to about 3% dark energy, which is on the borderline of what the CMB allows, then you see that these oscillations really aren't there at all. And so people who say, well, why should you be dealing with monotonic equations of state? There can be oscillations. Yes, there can be oscillations, but even in the models where you expect to have oscillations, they can often be damped away very, very quickly by other observational constraints, such as the early time conditions. So this is what these exact W of A's look like in the phase space plane, W versus W prime. So now A is simply a parameter, the scale factor is simply a parameter along these curves. And again, it's the same two cases here. The dash case is the one where you have a lot of early dark energy, so you're starting at W of 0 at high redshift, early dark energy, and then you get this strange behavior. It even starts heading away from lambda. As you can see here, it's going up to positive W's, and then it comes around, and then you have these oscillations, and it eventually settles into that minimum and becomes a cosmological constant. And I've color-coded it here, so the black curve goes, I think, around to redshift 2, maybe? I forget the exact ones. And then at redshift 1, and then redshift 0, and then to the far future as well. But you can see that the black curve, the one that has a reasonable amount of early dark energy, you don't have all these loops. It basically goes straight in toward the cosmological constant. So again, you can just solve in your computer even quite strange cases of dark energy. One of the interesting things to do when you have this autonomous system of equation is you look at what's called the critical points, or the stationary points for this, and we've seen a number of contributor talks about this. And that's where the derivatives are 0. This does not tell you what the dark energy is doing asymptotically. These are mathematical points. The dark energy dynamics, the path of the dark energy, may never actually go through these points. To figure out what those are, you have to do a stability analysis. And again, this has gone through in this Copeland-Little-Wands paper, where basically what you're doing is you're taking the vector of x and y, which I call p here, and you're solving just through linear algebra a stability criterion. You perturb it, and you then have a matrix, and you look at the eigenvalues of that matrix, and that tells you how you actually approach that critical point. Are you attracted to the critical point? Are you repelled from the critical point? Do you circle around the critical point? And that tells you about the stability of the system. So there are two applications, several applications to this. People who are very worried about the coincidence problem ask, well, asymptotically, do you go to a finite value of the matter to dark energy density ratio, for example? It's also very relevant to asking what the fate of the universe is. So I've shown two models here. The linear potential model, Linde's model of just rolling straight down a slope, and the PNGB model, the pseudo-scalar axion-like model. It's basically a cosine potential. And I've arranged it such that in the WW prime plane, all the evolution from the infinite past to today is this little line segment here. And I've arranged it so that they both have the common value of W today. W naught is about minus 0.78 for both of the models. And you can see it's extremely hard to distinguish, even if you blew up the scale, between these two types of thawing models through observations from the past to today. But in the future, they have extremely different fates to the universe because they have extremely different critical points. And so the linear potential, as I alluded to, gives you a cosmic doomsday, that you run off to negative potentials and eventually you have a recollapse of the universe. And so W just runs off to positive infinity. You get this collapse and this singularity. Whereas the PNGB oscillates around the minimum in this cosine potential. And here you see the oscillations just keep going around and around and around. And again, you can get this through the stability analysis. Another interesting application, which I came across recently, is a lot of people worry about crossing W of minus 1. And I've never quite realized why people find that so fascinating. But that's a separate issue. It's not really a physics issue as such. They love models where W crosses from greater than minus 1 to less than minus 1. And it turns out that you can do a very general proof without solving the equations at all, just by looking at the form of the equations as to whether certain fields can or cannot cross minus 1. And so let's go back to the y equation, the square root of the potential, and let's look at the critical point for that. So we're not solving the potential, we're just asking what is the asymptotic behavior where y prime equals 0. You immediately get this equation out, and we can recognize that the logarithmic derivative of the Hubble parameter is the total equation of state, given in this particular form. So for a phantom field is one where you have a negative kinetic energy term, so it likes to roll uphill. And so you have your potential, it rolls up the potential instead of rolling down the potential. And so V prime is a positive quantity, and so that tells you that asymptotically, W total has to be less than minus 1. So a phantom field stays a phantom field asymptotically. It does not cross minus 1. So this is completely general. You do not have to specify anything about the phantom field. It even applies if you couple the phantom field to the matter. So this is a way you can analyze the results without actually solving all the equations. The one caveat is this is the asymptotic behavior. You're saying it's starting negative 1, it ends at below negative 1, but it could actually cross in the middle. So this analysis only tells you asymptotically what happens. You actually have to solve the equations to understand the intermediate behavior. On the other hand, you cannot argue the other way, that a quintessence field with W greater than minus 1 can be that way. There, V prime is negative, and so that tells you that W total has to be greater than minus 1. But that doesn't tell you that W of the dark energy has to be greater than minus 1. And so you cannot use the converse that a quintessence field cannot cross minus 1 just by this simple argument here. And in particular, if you couple it to fields, then it's fairly easy to make it to cross W of minus 1. OK, so you have dynamics. We still need to tie it to the observations. So the Fisher matrix is a very common way of doing this. And this is basically a simple version of a full likelihood analysis where you're saying that around the best fit point, you are parabolic. Okay? You're near the extremum and you're ideally the minimum, and you're parabolic near that. And again, you should see these references for a detailed explanation of it. So the Fisher matrix is related to the log of the likelihood. You're taking derivatives with respect to parameters. So you have a certain parameter set. It could be W naught, WA, omega matter, whatever you feel like doing. And it involves these what I call Fisher sensitivities, these derivatives of an observable with respect to a parameter. So it could be a derivative of the matter power spectrum, derivative of a supernova distance, derivative of a CMB multiple spectrum, and so forth, with respect to a parameter. And so the more your observable changes as you change the parameter in your model, the more information you have from the observations. So the Fisher matrix is often called the information matrix. So if these derivatives are large, then generically your experiment will give you more information on the model. You also have the error matrix on the observations, so the inverse of the covariance matrix of the observations. And then there's the famous Cramer-Raoult theorem, which gives you a limit that the actual uncertainty on the parameters is always going to be greater than or equal to the inverse of the Fisher elements. So the simplest case here, let's just do a two-dimensional Fisher matrix. You can have n parameters. Let's just do 2 parameters. We've got a certain set of observables, for example, luminosity distances at certain redshifts. Our covariance matrix is again the error matrix here. And so this is basically just delta d, the error in your observable. I've written it as delta d over d times d because often people phrase it in terms of magnitudes, which are delta d's over d's. And I've made it a diagonal matrix. In general, there will be covariances between an observation at one redshift and another one at another redshift, and that's taken into account here. But in the simple case, I've just made it a delta function. So then the Fisher matrix becomes very simple. You just have the omega omega term, omega w term, for example, and so forth. To get the errors, you just invert that matrix, and these elements are the uncertainties on omega, uncertainties on w, and the covariances between the two. So once you have these uncertainties, you can plot them up as a likelihood contour, and it's pretty trivial to translate from these uncertainties along with the covariances to the shape and the orientation of the ellipse. It just, for example, the orientation involves tangents, and the axes, the major and the minor axes, are just these diagonal elements. So again, it's called, remember, Fisher means information. Okay? The more information there is in your data, the larger the Fisher elements are, and the smaller your errors will be. To add data sets together, you just add the Fisher matrices. You're just adding information together. If the data set 1 and data set 2 have some overlap in the information they contain, then there's going to be covariances that are included there, and you don't want to double count the information. And so that has to be taken into account. If you have external information rather than data, you just have a prior, then you can make a matrix that represents the prior. So for example, if omega matter is, if you're saying that it's 0.28 plus or minus 0.03, then you can just put it in to this log likelihood in terms of this sort of a chi-squared, and that just gives you elements in the Fisher matrix then. Okay, so again, that's pretty familiar probably to most of you. Otherwise, see these for more details. So again, once you have the Fisher matrix, you can start plotting it up, making these confidence contours. In general, you have n parameters. You'll have an n-dimensional ellipsoid. Because of the parabolic approximation, you will always get ellipses, ellipsoids out of them. You won't get banana shapes, for example. You have to do a full likelihood calculation for that. Often, you don't want to look at n dimensions at once. There are some parameters that you want to concentrate on, and it's hard to look at more than 2 dimensions at once, although there are some interesting 3-dimensional plots out in the literature. So you have to marginalize over those extra parameters. Again, in a full likelihood calculation, you can go through, and there's statistical subtleties in minimizing versus marginalizing, which I won't go into at all. So to marginalize in the Fisher approach, it's extremely easy. All you do is you invert the Fisher matrix to get your errors, and then you just ignore the parameters you don't want to deal with, and you only plot up the part of the inverse Fisher matrix or the covariance matrix that you do want to plot. And that marginalizes, it integrates over the probabilities of the other parameters. And that's generally what you want to do. Sometimes, however, you want to fix a parameter. So for example, suppose you extended your parameter set to include, let's say, the mass of a neutrino. And you also want to see what it looks like if you fix that. For example, you fix it so there is no mass to the neutrino. It's 0 always. Then you want to fix the parameter. In that case, what you do is you ignore the row in the column in the Fisher matrix rather than in the inverse of the Fisher matrix. You plot up your contours at various confidence levels. You can look up in tables what the delta chi-squared corresponding to a 1 sigma joint contour, 2 sigma joint contours, and so forth are to put that value in the plotting program. And you will get contours like this. If you have a contour in a paper and you want to find out what the 1 sigma value is, if they don't tell it to you specifically, you just divide the length of the contour by the square root of the delta chi squared. And so it's a nice habit to have. You stare at something like this and you say, okay, the uncertainty in W, it looks like about 0.15 or so. And so I just divide by basically 1.5, and sigma of W is then 0.1. It's nice to be able to just do that very quickly in your head as you go through the paper. So the narrowness of the ellipse, the axis ratio, or the ellipticity of the ellipse, tells you how much covariance there is between the quantities, as well, and the orientation tells you the type of that covariance, basically. Again, observations can have different directions. They can be complementary to each other, so that the joint estimation is a smaller contour. In this particular case, the smaller contour is just about the intersection of the ellipses. But it doesn't have to be, because this is actually n-dimensional ellipsoids. And so the intersection in n dimensions that you then marginalize does not have to be. It can be, for example, smaller than this. Okay. Your observations aren't always perfect, and your theory isn't always perfect as well. And so you might ask, well, suppose I made a mistake either in the data or in the type of model that I'm trying to fit to this. How do I tell what the error is in that? How do I tell that not the error due to the quality of the data, but the actual sort of offset of the data? So Fisher analysis can do that as well, give you the bias. The formal expression for the bias in a parameter P is given by this. It's basically, again, linear algebra. You have some offset in your observable. There's then some matrix that hits that, and that tells you what the offset in the parameter is, the bias in the parameter is. So it's related to these Fisher sensitivity derivatives, again, to the error matrix in your data, and the actual offset either in your observable or in your theory model. So again, let's do the simple case where the covariance matrix is diagonal, the error matrix is diagonal, and then you get a form that looks like this. It's basically something that looks almost like a Fisher matrix times the inverse of a Fisher matrix. The piece that's missing here is, again, that derivative with respect to the parameter here. And so that gives you the bias on the parameter. Because you have both dispersions and offsets, it's often convenient to combine them together. And in statistics, there's a particular parameter called the risk parameter, which combines them in this quadratic way. You're summing in quadrature the error due to that your data is not perfect, it's fuzzy, and also the error due to the fact that your data may be offset, may actually be wrong in some way. And so you'll often see papers talking about this risk parameter. Okay, so now we want to design an experiment. We say we want to test our theory. Let's actually design the experiment in some way. So you don't want to design it only for the precision. You have to beware of other things, such as degeneracies. Your ellipses, in dramatic cases, can actually become infinite bands. And so, for example, as we've mentioned, for the CMB, you have this geometric degeneracy. The distance to the last scattering surface gives you this basically infinite band in the plane, which gets broken by other physical effects. But it's still a pretty strong degeneracy in between these two parameters. So you can't determine any one parameter of these exactly, only a particular combination of them. But in general, you get something not quite so extreme. You get some ellipse in this plane. And then the things that you have to worry about are degeneracies in this higher dimensional space. So for example, if there's a strong degeneracy between constant W and omega matter, or with W naught WA and omega matter. And the degeneracies can often broaden the ellipses. Okay, so not necessarily exactly orthogonal to the major axis, but they in general broaden the ellipses, these degeneracies. So you have to take into account the full parameter set. And the other thing is systematic errors, which put a floor on how precisely you can make it. So you can make more and more and more observations, but they won't do you any good if there's some systematic error that doesn't let you use that information. For example, if you don't know the calibration of your detector, you don't know how accurate the detector is really counting those photons, then it doesn't matter how many photons you observe. There's what's called an irreducible floor to the precision, a systematic. And that generically elongates the ellipse. But the other type of systematic that I talked about was these offsets, where you've just got something wrong in your data. And those will then offset your result. And so any of these would still be consistent with that point. So if that's the cosmological constant, any of these effects, well, you would still say the cosmological constant is consistent, but these systematic offsets are very pernicious in that you might actually think you've ruled out that model because of these offsets. And so that's why you have to pay a lot of attention to these systematics. Okay, let me go away from the standard Fisher matrix and talk about some other ways of using the information. In particular, doing an orthogonal basis expansion. So just like you can do a Fourier transform, you can expand a function in a Fourier series and a Chebyshev polynomials and all sorts of things. You can generically just choose any orthogonal basis. And suppose we want to measure W of z, rather than putting a functional form like W naught plus WA times 1 minus A, suppose you want to allow it to be completely arbitrary, then you can expand in these orthogonal basis. So here EI of z are these orthogonal polynomials, and alpha I are the coefficients of each of them. And for the orthogonal basis, these uncertainties on those coefficients will be uncorrelated. And these are often called principal components, but really you can just do any orthogonal basis, and that's why I call this orthogonal basis. So you can start with just W in each bin, allowing that to float to approximate a smooth curve that can go up or down, be non-monotonic, whatever you like. So again, you start off with the Fisher matrix, then for those WIs, for W in each redshift bin, and then you look for the orthogonal matrices that diagonalize the Fisher matrix in that way. When you've done that, then the rows of the diagonalizing matrix are the eigenvectors. Okay? They are these EIs of z. But remember, Fisher matrix is an information matrix. If you are talking about different information, you have different Fisher matrices, and you will have different eigenvectors. So this is not, for some reason, this is not well appreciated in the literature. If you're trying to compare the principal components, the eigenvectors of a BAO experiment with the eigenvectors of a cluster experiment, different information goes into them. They are different eigenvectors. You cannot look at the first principal component of one, the first principal component of another, and directly compare them. Okay? It's apples to oranges. They're not the same thing. So you cannot directly compare them in that way. If you change the probe you're using, even if you're changing the experiment, if I do a BAO experiment out to redshift 1, a BAO experiment out to redshift 2, there's different information, different eigenvectors. You cannot directly compare them. So a good article to read is the one by Dragan Huderer and Glenn Starkman in 2003, which really first applied this to dark energy. And here you see some of the principal components. They start off fairly smooth with some oscillations, and by the time you get to the higher principal components, they have some very rapid oscillations, and they're pushed to the extreme ends of where your data is.
So is there any way to compare the models?
So there is. So I'll show that in a little bit. Another thing that you can do is say that I don't like these oscillations, okay, or I don't even like these, because here I've got what looks like a certain amount of weight at this redshift, but I also have some weight at that redshift, and one's negative, one's positive, so I can't really tell what redshift an effect is coming in at. And so you might want to try to localize the information at particular redshifts. And so people talk about these band powers or decorrelated redshift bins, where in any one redshift bin, the error on W in that bin is uncorrelated with the error in another bin. This works very well for large-scale structure, where you say, I want the band power at one K mode, at one scale, to be different than another K mode. But people have just brought it over to dark energy without testing whether you actually localize. And it turns out that for dark energy, you don't localize nearly as well as you do for large-scale structure. And so this is not actually a very useful method. You can decorrelate the bins, but you can't localize them. And it also depends very strongly on your assumptions. So here's, for example, the weights that you put as a function of redshift. And you can see that this first principal component basically, is reasonably well localized at low redshift. But as you go to the second one, it's less well localized, that this bin in redshift is almost the same as that bin. And by the third one, you see that you really haven't localized it much to the third bin, but the second and the fourth are almost the same. The situation is actually much worse because here they fixed some parameters. So they've restricted the information. And if instead what you do is you don't impose an infinitely tight prior on the equation of state at high redshift, then you see you change these weights substantially. And so you see you can actually get negative contributions now. And by the time you're at this third mode here, you see you've got this strongly negative dip in the first bin and to go with the peak in the third bin. And so you're not really localizing the information. The third component is not telling you about the third bin at all. It's a mix of all the bins. And so this method really is not all that effective. So let me go back to the principal components and talk about, what is that actually teaching you? You can measure these, you can calculate these uncertainties on the coefficients of each principal component. And people look at that and they say, oh, these numbers are small. I can find 10 or 15 principal components, and they're all small. But there's no scale to compare what is small. So they get 0.1, they say that's small, but small compared to what? Another issue is these are noises. Right? In astronomy, in physics, you have to do signal to noises. You don't just care about the error, you care about the error relative to some signal. And so there's, again, standard ways of doing this. The signal to noise, which is basically the signal, how big the coefficient should be, relative to the error in that coefficient. And you sum them all up and you take the root. That's the total signal to noise. You could also cut this sum off at some number of modes. Say, let me just look at the first 5 modes and look at the signal to noise. And so we've done this for a number of different models. And even with next generation data, you find that even though the sigmas of 10 or 15 components may be small, the signal to noises, the physical thing, is only greater than 1, much greater than 1, for about the first 2 components. And so here we've taken the most extreme cases, the cases where the highest components contribute the most. Okay, so this is the most optimistic you could be in different classes of dark energy models. And so for the freezing model, the most that the highest components can contribute above the first 2 components is less than 3%. The first 2 components give you 97% of the information. In the thawing case, 0.3% is the most that components 3 and above can contribute. If you start to go to really bizarre equations of state, ones that oscillate, that are highly non-monotonic, then you can get up to 14% in the third and greater components. But the point is, the idea of principal components was to say, well, maybe there's many pieces of information beyond W0 WA that I can use. And the answer is that very unfortunately, that's not true. That you really don't have any signal to noise beyond 2 components. You can choose those 2 components to be W0 WA or something else, but you really don't have much more than 2 pieces of information. So let me run down a list of common mistakes, things that really frustrate me when I have papers to referee. So hopefully this will decrease the number of mistakes out in the literature. I'll just go through them quickly. There are what we call nuisance parameters. There are sort of calibration parameters that you don't actually plot up when you're trying to do your cosmological parameter likelihoods, but you have to include them in the analysis. You have to marginalize over them. So that's the calibration scale for supernovae, the combination of the absolute magnitude and the Hubble distance. And for BAO, it's basically the sound horizon scale. You're tying things to high redshift. So you have to include those as fit parameters, which you then marginalize over. And an infinite number of papers just completely neglect systematics. They say, oh, we're going to observe 100,000 supernovae, and our error bars are tiny, tiny little dots. Okay? It's just not realistic. You've got to include systematics. Eventually, people have learned that they have to put the word systematics in the paper, but they don't actually put systematics in. And so if they're still square rooting down the errors, they're not doing systematics. And so you will see papers which say, oh, we do all these systematics, but everything still scales as the sky fraction that they observe or the number of objects that they have. Okay? That's not systematics. The word self-calibration has also been used beyond what it really means. Self-calibration means that you're adding fit parameters in to describe the systematics, and that you will then marginalize over that. And that's perfectly legitimate, but you have to remember that the assumption is that the form you put in for these extra fit parameters is the correct one. So if you said, oh, it's going to evolve as 1 plus z to the n, I'm going to marginalize over n, that's my systematic fit parameter, that's fine if the evolution really is 1 plus z to the n. But if it has a different form, then you haven't removed the systematics. And so you've got to remember that self-calibration is not a panacea. It's not something that just immediately solves all your problems. As I just said, for principal component analysis, don't use the noise. You have to use the signal to noise when you're talking about things. And you cannot compare principal components from one set of information to principal components directly from another set. And another bad thing to do is fixing W to any value. Commonly, it's done to -1 at high redshift. That's going to distort the principal components, as you saw. The other form of sins for parameter estimation is just being absurdly optimistic. And so here I've been as optimistic as I could be for the 3 major methods, Supernovae, BAO, and weak lensing. And so if you see a paper that's completely optimistic for one of the methods, you should just feel free to be as optimistic for another method. And so in particular, if you count every acoustic mode in the universe to give you your distance precisions, then you can get down to 0.1% distance accuracy. So shouldn't I feel free then to count every supernova that exists in the universe? One supernova goes off every second in the universe. Let me observe all of them. Okay? Then I get my distance measures down to 0.003%. Okay? There's a certain level of absurdity that you've got to check with reality. Same thing, full space weak lensing. If each individual galaxy is sheared by 1%, eventually you're trying to use them all. You're at the 3 times 10 to the -6 level. You know that there are tons of systematics, not understanding your telescope optics, your detector efficiencies, and all of that. Okay, so you've got to have a certain level of reality. All right, I've pretty much said all this already. Controlling systematics is the name of the game. So the interesting tension between observation and theory is not something new. This goes back to the mid-1800s, this quote by the Astronomers Royal of the United Kingdom. People often think there's only one Astronomer Royal, that Sir Martin is the only one. But in fact, each royal observatory that exists has its own Astronomer Royal. So there were 2 at the same time. One was an observer, one was an experimentalist. So you have these famous quote from the observer one, "I should not have believed it if I had not seen it." And then the theorist Hamilton goes and says, "How different we are. My eyes have too often deceived me. I believe it because I have proved it." So it would be very nice if we're at that situation in dark energy where the observers actually believe the observations and see it, and then the theorists believe the theories and say, okay, we've proved that it has to be this way, but we're not quite there yet. So let me talk a bit more about systematics now. I'll go through some of the supernovae. As I've already said, you get a rich variety of information. You get a spectrum, you get the flux versus time, and you can see the environment that the supernova is taking place in. So you want to use all of that to constrain systematics that you can come up with. Supernovae have been used for 15 years or so that we have a detailed list of what things can go wrong, what the systematics can be, and ways to address them through doing observations over multiple wavelengths, through getting spectra to cross-check, and so on and so forth. And so each method should have a similar list of things that can go wrong and ways to deal with that. So in particular, if you have good enough observations, then you can start doing cross-checks. You can do systematic tests, and in particular, you can look at, in this example, supernovae that look very, very similar to each other through all of the observations that you've made. So you've done detailed spectral observations, you've looked at the spectral lines, you've looked at the spectral velocities, you looked at the photometry, the imaging, where does it occur, what environment does it occur in, how bright is it in the UV versus the visible, and so on and so forth. And then you just put all the like ones together. You just shuffle off the sort of data cards into different piles. And then you do independent cosmology analyses of each set. And you should have the same cosmology for each set. And so the mantra is, if you use the same supernovae that appear exactly the same, but lie at different redshifts, that teaches you the cosmology. That gives you the curve of the Hubble diagram. If you then look at supernova at the same redshift, so they should have the same distance, and then you look from one pile of data cards to the other, then you're doing systematics control. And the idea is you need enough observations and accurate enough observations that you can do this. And this, again, applies to any method you want to be able to do that. So let me go through a specific example. Suppose you have a whole set of supernovae, and your observations are not good enough to see subtle differences between them. That one's brighter in the UV than the other, that one lies in ellipticals versus spirals, and so forth. And suppose those differences actually matter. Okay, if they don't matter for the brightness of the supernovae, then that's fine. But suppose there actually is some difference in the brightness of supernovae in ellipticals versus in spirals. If you lumped everything together in a Hubble diagram, in a single Hubble diagram, then what you would find is if there really is no evolution, then fine. You have a certain figure of merit. You have you've learned a certain amount. So this is basically the size of the contour in the W0 WA phase space. But as there really is some population drift, some evolution in the supernova properties, then the fact that you've lumped everything together in a single Hubble diagram degrades your figure of merit. Your precision stays high. You still have the same number of supernovae. You think you've done really well, but there's a bias. So this is a risk parameter here where I've taken into account the bias that you get for not realizing that there is this systematics. So now let's say our observations get a little bit better, that we can recognize, oops, just one at a time, that you can recognize the more extreme outliers. So then what you do is you improve this region to this red region. And the amount you improve depends on which set you actually can recognize. And that's why there's an envelope here, not a single line. Suppose your observations get a bit better. You can recognize the two discrepant sets. Then again, you see you get an improvement. And in particular, if you do recognize the two most discrepant sets, that's the top line. And the bottom line is the two least, the sets that deviate least from the average. So that you get this. And then suppose your observations are good enough that you have put fit parameters to each of the different sets that you have. Then what you find is you get these narrow blue bands up at the top if your observations are really good enough. And that's extremely close to what you get, if there was no systematics at all, what I call the perfect case. So where the curve intersects the axis here. There's about a 2% degradation. So the idea is with each extra subset you recognize, you have to add in fit parameters. And so your errors get worse, but your bias gets less. And so the risk actually gets better and better until you're within 2% of perfect. And so again, this is why you need good enough observations. You can't just say, oh, I found a supernovae. You really need all the spectral information. You need to go into the infrared and so on and so forth. For weak lensing, there are systematics as well. So this is a plot of the noise, the B modes in the weak lensing, which should not be there, the best that you do from the ground currently, and what you can do currently the best from space. You can see that these bright high peaks really aren't there with the space observations. There's a large advantage in systematics to going to space. That's the noise part. On the signal part, you get a huge advantage as well. You have much higher resolution. You don't have the blurring from the atmosphere and the shaking of the telescope under gravity and wind and so forth. So you have many more resolution elements to measure the shape of the galaxy. You can see, viewed from the ground, compared to a Hubble Space Telescope, you just get this sort of blurred out view of the galaxy. And your pixel sizes are much larger. For clusters, there's a number of different ways of detecting clusters. I've given 4 different ways here. The green are sort of the advantages of the method, and the red are some of the systematics that you have to worry about for the methods. And again, uncertainties that you have in measuring the mass, which is very difficult to do directly, only the weak lensing measures it directly, uncertainties in the mass threshold can actually go to quite strong biases in the values of the cosmological parameters. The last example of systematics I want to talk about is trying to stitch together different data sets. Instead of doing things with a single survey, you're stitching together different surveys or different instruments or different passbands and so on and so forth. This can give rise to bias, and you have to do your simulations to see how that will affect your results. And so this shows the bias relative to the statistical uncertainty in different parameters, W0, WA, and omega matter, if you're stitching together a supernova survey at low redshift to a supernova survey at high redshift. And so as a function of the matching redshift at which you're putting these two supernova surveys together, you will see you bias different parameters, but the lowest you ever get is about 1 sigma of bias, which you want to avoid. And that's why you really want a unified, homogeneous data set. And this applies as well if you're doing a galaxy survey. You want to make sure that the galaxy properties are the same in your different surveys. You might worry that as you go to very high redshifts, you're forced to stitch together surveys because a low redshift survey or a survey below redshift 2 or so is very difficult to do with the same telescopes to higher redshift. And so, for example, you might want to stitch together supernovae to gamma ray bursts if you believe gamma ray bursts could be calibrated. And you can see there's really no problem because there's no need to go past redshift 2. So this says, suppose we've mapped out the expansion history to redshift 1.5. How much do I gain by going to higher redshifts? You can see even for the most extreme dark energy asymptotic behaviors, so I'm going to let it go to matter domination at high redshift, or I'll let it completely vanish, go to minus infinity. So everything has to lie in between those. You're only getting sort of 1 to 2% distance differences. So unless your probe can probe better than 1%, then you really don't get any gain by going past redshift 2. And in fact, past redshift 1.5, almost all the gain is between 1.5 and 2, that from 2 out to 5, you're really not learning anything more because, again, you're basically in the matter-dominated era. So as a summary, how do you design a dark energy experiment? Again, you want it to be theoretically interpretable. You want it to be mature observationally. You change the redshift range, and that rotates the contours, breaks degeneracies, systematics control, complementarity through multiple probes, and using a homogeneous data set. If you do all of those, you can actually get very good constraints on this full set of parameters that I talked about yesterday or last lecture to be able to really probe the physics. So we're probing the matter part of the universe, we're probing the dark energy properties, we're probing the form of the gravitational deviation and the early time behaviors. So again, dark energy is not the only thing that's out there, and it may take a long time to solve. So you want your experiment, you want your mission to be able to tell you much, much more about the universe than a narrow dark energy question. So as the National Academy of Sciences panel said, you want a large discovery space. So within cosmology still, there's a lot of things that you discover with a mission that's good at getting dark energy. So you learn a lot about inflation as well. For example, the tilt of the primordial power spectrum with the same observations you use for dark energy. You can probe non-Gaussianity through cluster abundances. You get maps of the dark matter in the universe through weak lensing, for example. And again, space has this enormous advantage in that you have much finer resolution and you can extend into the near infrared in such a way that you can actually get 40 trillion color resolution elements on the sky. That's a lot of data that you can play with even if you don't care at all about dark energy. And that's 20 times more than you can actually get from the next generation ground experiments. Okay, so the plans for actually doing these space-based dark energy experiments are doing a wide survey. So you want a survey that's of order 10 to the 4th times the Hubble Deep Field, even deeper, and then a survey that's almost as deep, but about 10 million times wider. So that's pretty impressive. You want to map deeply back in the history of the universe, and you want to do it over multiple wavelengths. So within the United States, there's the Joint Dark Energy Mission, a joint project of NASA and the US Department of Energy, and it's baselined for launch around 2015. In Europe, there's the Cosmic Vision program with a Euclid concept for a dark energy mission. And we'll see in the next year, we expect to hear developments of both of these projects in the next year to find out when they will actually launch.
With this mission, what will be the farthest supernova that is coming?
So it's about what I showed, this 10 billion years. So about redshift 1.7 is what the scientists are hoping it'll be. We'll see what it ends up being in the end. So again, to sort of summarize a number of the points I've made in my lectures, we don't know that the answer is lambda already. Okay, that's the main thing that you should take away. And we basically don't know anything about the dark energy properties at redshift greater than 1 with current data. You shouldn't assume that theoretically lambda is the only game in town or even the favored game in town, because we failed for so long to understand it, and that we know that inflation, the one other epoch of acceleration, was not a cosmological constant. You need to have better experiments to look at the time variation, to look at the dynamics, and you want to control the systematics. You want to combine different types of experiments. So we've heard a number of talks talking about the gravitational modifications and how you need to distinguish those from a physical dark energy through both observations of the expansion history, distances, and the growth of structure. And again, you want to reduce the systematics. When you do these, it's not only good for dark energy, you get a very rich variety of astronomical resources. So you get these, as I said, sort of 10 million Hubble deep fields out of this. Okay. We have a number of incredibly interesting questions to address. And it ranges everything from the nature of quantum physics to the nature of space-time and extra dimensions. So there's a lot to be able to do here. There is a contingent that is very pessimistic about dark energy and basically says that we won't learn anything about this very challenging, very difficult subject to deal with. And in particular, a little less than a year ago, there was a symposium at the Space Telescope Science Institute, and there was one talk there where he sort of made his trademark being pessimism about this. And the great thing about being pessimistic, saying we will never be able to learn something in science, is how spectacularly it fails. So in 1835, Comte said, you know, how can you possibly ever learn about the composition of stars? They're so far away. How are we going to do that? And not only does it fail so spectacularly, but it often fails so quickly. So after Comte said this, it was only 14 years until the methods were developed to figure out how we know the composition of stars. And so if you project forward 14 years from now, and so as we go forward to cosmology on the beach 14 years from now in Fiji, then we can look forward to a rich variety of talks explaining, okay, this is exactly what dark energy is, and this is you know, the nature of the dark energy. Yes. Yes. So I think we need some people to come up to tell us.
We all want to change the world. You tell me it's we all want to make you stir. But when you talk about that reaction, don't you know you can count me out? Don't you know it's gonna be alright? It's gonna be alright. You say you got a natural solution. Well, you know, we all love to see the plan.
You're blocking the screen. You're blocking. Jorge, you have to move back. You want value anthropic. All I can tell you is, brother, just drop it. Don't you know it's gonna be all right? It's gonna be all right. You say you'll change T mu nu substitution. Well, you know, we all want a scalar field. You tell me it's GR modification. Well, you know, we all want our brain revealed. But if you go coupling terms to R mu nu, the equivalence principle is gonna get you. Don't you know it's gonna be all right? Gonna be all right. You say you want holographic condition. Well, you know, we all want decreased degrees. You tell me it's a phantom action. Well, you know, you better remove those please. But if you go carrying pictures of Calabi, yeah, you ain't gonna make it with anyone anyhow. Don't you know it's gonna be all right? It's gonna be all right. It's gonna be all right.